write a relation once, and it's just constraining all the parameters of the relation building. There's no distinction now between input and output. All the parameters are constrained somehow. And you can get multiple behaviors out of the same definition, out of the same relation. So this is something we want to use for semantics. So for example, you can imagine writing, expressing the rule of your type system, get a type inferencer, get a type inhabitor, get things like this, and we'll show a baby version of that. And you can imagine writing the evaluator function, like the evaluator, like the EVL function we saw last time, the JAR function we saw last time, and writing it as a relation. And even though it's for a functional language, by writing it as a relation, you get relational behavior, you are converting functions into relations, you're able to do synthesis over this semantics that is represented by your evaluator. So we'll see examples of this today, and maybe there's quite, the language I'm going to show is called mini canon, and it's a particular kind of pure constraint logic programming language. And the fact that it's pure made it able to do these uncompromising things of running in multiple directions, running in partially instantiated terms, and that's kind of what gives it its power as well. And so there was a book that came out, that's actually the second edition that came out more recently. And it's, this is from the co-creators of the language, so Dan Friedman, William Bird, and Kisayo, and Jason Heyman did the microcanon language, which is a great point to kind of get acquainted with like just writing a relational programming language using pure constraints, pure functional programming, and it's the implementation is basically 50 lines of code, and you can get into it the same. Okay, so let's get started. What it looks like to do canon coding. So first, I think I want to just introduce all the language features in one example that is fairly canonical. And we can come back and maybe analyze the programming constructs separately. But before we do that, I just want to define the append function in scheme. So you could define it like this. If no S, then comments cars and then so it's recursive in the first argument, and we can define it like this. And then you can do something like append. I shouldn't have redefined the built-in append. That's not very good, but I guess I will just show you an example. Here you can do this, and then do something like that. So that's just, let me just call it my append to and now I can basically try to turn this into a relation, and that's also a very sort of a one-on-one example in Prolog how to do append functions. But if I turn it into a relation, I can do defra my appending ls and s. So now I have an extra argument, which is the output of the appending. So I have three parameters now, ls and ls. And I can do like a condi, which is similar to the condi we've seen before, but relationally taking non-deterministic branch. So here is one branch. If we can unify L with S, so unification is another idea, but we have this way of comparing element and instantiating logic variables as needed. I should come back to this. And then here I can say S is LS, unifying that and that. And in the other case, I'm introducing new logic variables A and D. And I'm saying const AD is L, so I expect some sort of list. And then I can say const A DS is LS, so I'm introducing DS as well. And now here I can do the recursive code, my append row, which is going to take D, S, and do DS. So what have I achieved when I okay, that worked. So now I have this relation, and I can do a run to interface with scheme, and I can just call it like I did before, and say we have A, B, C, D, and then the output is Q, so Q starts as a fresh logic variable. I do this, and I get indeed the output A, B, C, D, E, and it's in a list because I might have a list of this one. Let me just change the printing of expressions to be just like that, so we have that. And now that I have this, what else can I do with this relation? I can decide to maybe put a logic variable somewhere else. So, and now I get ABC, so I was able to run it in another direction, or I can also ask for say, all the inputs and outputs such that this holds. And here I get only one result, but I can ask for 10 results and I get all the results that are possible. And that's also for the other star. So any questions so far? Is there any one of these primitives that we should develop? So the primitives are condy, unification, recursive calls like to call the relation, and it's fresh to introduce logic calls. So just to give a little bit more about unification, first when you start a logic variable, you can say 1 and 1, and then this unifies, this 1 and 1 succeeds, and you get this thing here, this underscore dot 0, which represents a fresh logic variable. It could be anything. It doesn't matter what Q is, this goal is succeeding, the goal of unifying 1 by 1. On the other hand, if I do unify 1 and 2, I get a failure, an empty list, regardless of the logic variable Q, and I can also do 1, Q, and here I get the result. So this is how things get going. And condy, for example, would take 2 branches. So I can have a condy where I say Q is equal to 1, and Q is equal to 2. And then I get at list 1 and 2. I have 2 ways of getting success. Either I take the first branch or I take the second.
What was the E in condy? It's like condition of either one? Or
that's just the North Convention. I would need to ask on that one. I'm not really sure. Okay. Usually there is this convention that like any relation you kind of just name it with the O at the end. I don't know why condy got the difference. It's kind of historically there were multiple versions of condy. There was condy, condy, and condy. Yes?
In the condy example, the 1 and 2 being our 2 options is because those are the other things that we have instantiated in this relation. So
yeah, so I could also add a third branch. I don't know, I mean, I think it won't do anything super smart and simplifying, but if I add a third branch, then I get 3 options. And they're kind of redundant in the sense that they're only included in the third, but we've been explicit about the 1 and 2, so we explicitly have it there. Yes? Yeah, so this is first order unification, and it goes deep into lists, but it's completely different. So in terms of the unification, there is even like a simple implementation of unification where we just consider lists, right? So we have, if we have variables So if we have exactly the same variable, then we don't change the substitution. If one is a variable, but then we extend it, we have a substitution map and we extend it so that it has the other and symmetrically, and then if we have pairs, we recurse in the unification and we thread the substitution map. And otherwise, things must be structurally equal to them, like equal as values. So it's a very simple definition of unification. That's the one in Metaprogramming, but the one in this faster version is not that different conceptually. Yes?
So how does it know not to just get underscore 0? Because I was
Well, I think it would have been smart if it had done that, right?
Oh.
Because it would have subsumed the answers better. But it just mechanically goes through the condition and considers the option. Yeah. Okay, so this is a simple example, a very one-on-one example of turning a function into a relation manually and seeing the features of the simple constructs of independent. I mean, this is basically the language. There are additional things that we can see as they come along. So, for example, you might have type constraints, like is this a symbol, is this a number, things like that. So it's symbol, number. And there's like a constraint to check for the absence of information, absento, and these are Yes?
Oh, what do you get if you do like a run star, but you don't find any variables and the condition is successful?
Yeah, so I think I had this example here. Where should we change it? So you just get this one.
Oh,
This is saying the logic variable can be everything. Now, there are tricks. So, for example, you can define always no, for example. So let's just define it to take no argument, which is kind of weird, but and we can say 1, 1. As the second condition. So we can have that, and I'm not going to do a run star, but I'm just going to do a run 10 of always no. So we see here that it's not trying, it's going to be infinitely successful, and that's going to cause divergence if we did a run star. And it also kind of causes divergence even if you have a failure afterwards. So say, for example, actually, if I did this, this is going to. So what will happen here? So it's maybe let's even do as 1, 1. You will see that it and the problem is that it's generating infinitely more many possibilities in the first case, and then kind of saying they fail in the second case. So this by itself, if I run it, it's kind of like not very dramatic here, but this is an infinity, and because it's kind of generating a lot of successful things with the always so, and then kind of ruling them out one by one. Does this make sense?
So it's trying always so, and then it's finding the 1 equals 2, so it's like, oh, this always so doesn't work, so let's try a different one.
Yes, and the always so are not very variable in this case, but you could make that more variable. So this actually happens. I'll come back to it when we talk about writing a relation to look up a variable in the environment, like we did in the previous lecture. So if you have an environment that is not completely instantiated, you might run into these tricks where you're generating like bindings for your environment, and then they're not acceptable for the rest. So maybe let's look at this now. It would be a useful example. So let me see if I have test. So this is lookupable. So this is kind of using quasi-quote syntax, but it's not very different from thinking of an association list with the environment like we saw last lecture. And it's kind of making sure the environment matches between the first binding. And if the binding, if y is equal to x, if the variable is found, then we set the output the value found in the environment. Otherwise, we do it recursively. And so this is a useful relation. Let me just evaluate it. And consider lookable
You're using the old factor.
So we have this, oops, that didn't work. I put them in the wrong order, so this divided this first. Okay, so we get 2, right, as we would expect. But if I did something with an environment that was fresh here, and I said Q has to be equal to 2, then it's making up this environment, which is correct, but I can ask it for like 3 answers, and it's going to make up bigger and bigger environment with some side conditions and things like that. So this you can see that it's already problematic because this relationship which arises very naturally itself has this infinite generation aspect. So if I did this and then had some sort of fading condition afterwards, this will also be divergent. Yes?
I'm confused as to how it comes up with like a fresh environment. Because it seems like it's like not just random.
Yeah, so it's kind of following. It's a little more subtle than this, but initially you can think of it as going through the relation here and following those constraints and following the constraints in each branch. So it can say. So if you look at the 3 examples it came up with, it found this branch, and then in the second one, it used the other branch, and you can even see the equality constraint. So it's one way to think of it. But actually, the way the search works in Metaprogramming is that it's an interleading search that is complete, and it's not too hard to see in the baby version, the microcanon version, how this happens. So basically we have kind of this idea of a stream that can be either just the empty list, or it can be a procedure which is represented as it's kind of a clunk, so a procedure of no argument and you force it when you apply it, or it can be a pair. These are the 3 ways it represents things. And then I think the key part of the search that makes this not depth first search but something much more interesting is here when we have a punct, we actually switch the order around to give so here we have the 2 instead of the 1. So we switch the end and the beginning. We switch the 2 arguments around when we're exploring a punct. And that is causing, this small change is causing the interleading and giving powerful, basically modulo this divergence, it often can find a solution to things. So I will show one example of this. This is the lookable function here. And if we define a little bit more, we can define an interpreter in the same style as we've seen last time for a small subset of scheme. And this interpreter has a quote. So that's the first case. We're saying, is the expression a quote? It supports shadowing, so we make sure that the environment is not redefined quote. And it also doesn't want to use our value representations, our value for closures as expressions in the quote. So this is ensuring that the tag closure doesn't appear in the value. And then it's saying, okay, if you have all this, then the result of the evaluation, so here we have an expression, an environment, and a value. Recall that this is different from what we saw last time. Last time we only had an expression and an environment and we were returning the value. Here we have the output value as a parameter. And here we're saying in the quote case, v is equal to val. And then we have a case for lists, so we are supporting writing things like list 1, 2, 3, for example. So then we have the list 1, 2, 3. So this is creating that effect, or it can be more sophisticated with sub-expressions. Then we have a symbol, which we look up in the environment using the lookup function we found. Then we have the application case that we put first here for some reason. So the greater is the closure, and the rand is anything that evaluates to an egg, then we extend the environment and evaluate the body. So that's like a first order representation of how to deal with closures. And then here we have, in the case of closure, we basically unify the value with the closure argument. And so by this interpreter, and with a few auxiliary definitions to make sure that our expressions are intact. So for example, now we want to handle, where are we using properties here? We are using it here. We want to make sure that this is actually properly, this argument is properly at least something like this. So it's a simple structural traversal. And now we can basically, so let me just evaluate this. And now we can basically just run this, I guess this gives it away, but we can run a simple expression that says, give me an input expression such that the output expression is the same, basically. And in this simple interpreter, we immediately get a result. And if I look at what this is, if I look at this part, and I can put it in, because the other stuff is the side conditions, I can evaluate it in bracket or scheme, and I indeed see that I get the same thing. So we get a quine, and we can get many quines. So it's kind of like a nice generator of terms. In this case, with a peculiar constraint that is usually pretty hard to do manually. Like, even if you had to manually think of generating a quine, it's not an obvious thing. Unless, of course, you think of one as a self-evaluation. Yeah, so this is one example of something like that. And another example I want to show is the, yeah?
When you ask it for a quine, what stops it right now from just giving you one, thinking of one as self-evaluating?
Yeah, so this is a very good question. So this language doesn't have numbers. Yeah. So that's puts it out. But yeah, if you added numbers, if you can add a case for numbers. So there is a constraint for numbers, so it's not too hard to add. You can do X bar like this. Yeah, it sounds right. So I'm adding this case. And now I imagine, especially since I added it at the top, if I did this one, it generates a number. But if I ask for 2, it should generate 3. Any other questions about this? Okay, so this example also gives an idea of the kind of features that are in the language. So we've seen already most of these features, and the one we haven't seen is absento, which basically does something like so this will fail, but this will succeed. And so these are extra logical constraints that are, it's useful to have an expanding repertoire of those. So like, for example, one thing to palliate the issue with the lookup code that it's kind of too generative and substantial, it's going to look at never-going lists, is to use constraints and to really have a constraint domain which is just environment and treat that very specially. And we're also working on like, we can work on like having set constraints and things like that.
If you put a constraint that the environment is no bigger than like list of length 3 or list of length 4, would that stop the religions, or is there still a lot of room for variation within that constraint?
I think that would stop it for this particular case. It's maybe not very principled, right? It's kind of in practice, it's kind of hard to know when to do these kinds of restrictions, but also you would do it by basically kind of shaping up the form of your environment in advance. That seems that not more so difficult. Okay, so another thing that I want to show before we look more closely at interpreters, and I noticed like this language here for the query is basically an evaluator like we see last time, focused on this mini language with just the quote and list and lambdas. And so you could build it up to something that could evaluate append, for example. So you could build up your evaluator so that you could functionally evaluate the append function. And the question is, what happens when you treat it in this relational interpreter? And you get back this behavior at the end. So you get but maybe another example that I want to show that is also pretty well known in Prolog, in logic programming, is to kind of build a small type checker and basically get a type inhabitor, like inhabiting a type for free and things like that. So for example, here we have this typing relation. So X in environment M, this expression has type T. And now we have a lookup that is actually operating on this association list of variable to types. And then we have a case for when we have when a lambda becomes a narrow type. And then we have a case for the application where we have to make sure the type matches and things like that. So we can have this. The lookup for definition is the same, this is the same. And now by doing this, we can basically generate these terms. So maybe it's easier to see their output here. So we have generated basically this expression has this term in the empty environment. And so, for example, we see the identity function has the term something, arrow goes to the same thing, and so forth. And so we generated a bunch of those pairs like that. So I think there is a chance to scale this up a little bit, like even thinking of say when you're using a proof assistant like Rock, you are defining your rules as relations somehow, but you don't give the same computation power as you would get here. How can you combine these things in more specific?
To go back a bit, could you explain what absenta is again, and also like why it's important?
Yeah, that's a good question. So absenta doesn't really show up here. Let me see what it should. So absenta showed up in the other examples. It's not. I mean, it's not that fundamental, but it's really that we kind of. So we don't want our system to create closures by quoting. We want the only way to create a closure is to do a lambda, and then you get this tag thing, this specially tagged thing that represents a closure. So you don't want quote to have to be able to quote your internal representations. And so this is why there's an absenta here. And I guess for this one, it's just a restriction somehow that we don't want absenta to also occur. Yeah, so basically it has to do with like not wanting the internal representations to be quotable. And the reason this was specifically important for this one generation was that it would generate things with quoted closures in them that were not things that you could write and scheme as a quad. So this avoids that pitfall. And what absenta does is really make sure that basically here, if I have something that is like closure X, Y, Z, and I do absent or closure, this will fail. I'm not able to do that, not able to get that term. So it's a very simple check of like, does this subterm occur anywhere in the term, as a term or as a subterm? Yes? Yeah, so I think it might be more fancy than a curse check. So I think if I had something, I think it's similar. So a curse check would check if like a variable occurs in a term, and I'm not sure, but I think here we can do something more fancy. So we can have a list here, but I'm not quite sure. For the purpose. Yeah, so this also didn't work. So for the purpose of this example, the way we're using closure as a tag, I think an curse check could also work. It's kind of the opposite of an curse check. Right? Yeah.
One question about the infinite looping when you have the infinite one in the front and the failure in the second. Is it because it means that maybe the first part is the blame for the failure in the second? So
Yes.
if you try to write first one second.
Yeah, it means there might be a dependency there, even though there isn't. So there could be work to improve that analysis and say there's no dependency. We know that it will always fail. Fail finally. Another example where this happens is basically you have a conjunction, and if you flip the order of the conjunction, then you would actually fail finitely, right? So for example, if I go back to this example and just flipped it around, so that fails finitely because the first part always fails. So there is, semantically, it shouldn't matter in which order we do these things, but in practice, it does matter for divergence, like to get non-divergent behavior. And so this is one thing that is a very important problem in any form of non-determinism, is how can you flip the order of operation without degrading the performance. And also, like, I did play some trick here by like putting this recursive call last. It's kind of just best practice to do that to have the best possible divergent behavior, because you can constrain this more heavily if you don't have it. So this is a little bit of an art, but it should be more automatic. Okay, so let's see how we're doing with that. So we saw that